you very much, Paul.
Thank you, everybody. I hope you enjoyed the presentation today. I just want to talk to you a little bit about how we solve the large-scale data center cloud interconnection in our data centers. I'm going to talk a little bit about Equinix at the beginning. I think most people know who Equinix is, but what I would say is that when you think of the cloud and all the data centers that everybody talks about here, all of them have another piece of the architecture, which is an edge that connects to all the networks and all the users who want to connect to it. So just imagine the billions of dollars of investments going in every quarter to build these massive data centers, and all of them have to go to a place to connect so that all the traffic from all the eyeballs, the billions of users, all enterprise customers can connect to them. And you could see the kind of problem we started to see at Equinix the last few years. And I'll tell you a little bit about how we solved it with something called Cloud Exchange, and then what we see happening going forward, which will be a significantly bigger problem to be solved as we go forward, which is why we think TIP and OCP are very important. So Equinix, we're the largest retail data center company. We have almost 180 data centers. Yesterday, we announced the completion of acquisition of 29 more data centers from Verizon. So we have now a data center, 180 in 44 cities around the world. So you see all these red dots. And inside the data centers, we have presence from all the big companies of the world. So we have 1,400 networks. Every single company is considered one, although somebody like an AT&T or Verizon would be inside, let's say, 40 or 50 or 60 of our data centers. But we'll just count it as one. And we have 2,700 clouds. So Facebook would be one. Salesforce.com would be one, just to give you a sense of how many. This number didn't exist before. 4 years ago, it was almost nothing. Now, one third of our revenues comes from cloud, which makes up 2,700. And the networks continue to expand. Even stuff like satellite technology and all these wireless is all coming to data centers like ours. So this is our global platform. We call it retail because it looks a little bit like a mall. This is my best way of putting it. We don't have anybody taking massive space. People come take very small cages, maybe the size of this stage or twice, and put the edge of the network so they can connect to other people with fiber and to be able to get to the whole world. And our interconnection platforms are 3 types. We have fiber cross connects. Most people get fiber cross connects, the vast majority, because they want to control their own optics and want to be able to put whatever high speed they want when they connect to someone else. An example would be if somebody like a big content company like Netflix, and you have somebody like Comcast, for the users of Comcast who want to get to Netflix content or vice versa, they would get massive amount of fibers between them around the world to get the content inside our data centers. We do have internet exchanges, IXs. I think everybody's very familiar with that. We have the largest set of internet exchanges. And then we created something called Cloud Exchange to get to all these new IaaS, SaaS, and PaaS cloud connectivity, mostly for enterprise. And that Cloud Exchange is the thing we did recently to solve that I'm going to talk about. But what I would say is probably 70 to 80% of the world's internet traffic does come through our data centers on a global basis to connect. So that gives you a sense where we sit in the world, and we really are that connection point that everybody goes to. The growth continues to be very significant, not just from fiber cross connects, which is the middle, but you could see also from virtual cross connects, which was created in Cloud Exchange, as well as Internet Exchange. And we see that continuing given the number of players are getting bigger, the number of locations, as well as the traffic is bigger. One thing you don't see here, inside the cross connects themselves, people are going from 10 gig to 100 gig and even 400 gig with the same exact fiber. So even if you don't see the number of fibers are going up, we're seeing 10 to 20x volume happening inside our data centers, just as people shift to new technologies. So this is the problem set that we needed to solve. Essentially, Equinix, and a lot of people know who we are, 4 or 5 years ago, was a large-scale layer 2 interconnection company. People came and got VLANs between them to exchange internet traffic, and they got from us the ability to get a lot of fiber and connect all their ports on their IP switches. So we were really the plumbing for public IP peering. But we didn't look inside the traffic. We do offer some internet services, but for the most part, we gave people VLANs, and they did their own peering and exchanged their own traffic. What we needed to solve is that when the cloud showed up with IaaS products, and the first one of them was AWS with Direct Connect as a layer 2 product, the complexity became very significant, and the new set of requirements that started to show up were completely different than what we were designed for as a company doing just layer 2 VLANs. So people wanted dedicated, secure layer 2 virtual circuits, but they really wanted a flexible set of features because every cloud has its own features, and also different service providers and enterprises coming in want to be able to customize that layer 2 interconnect. That's a requirement we didn't see before the cloud started to show up. And the second thing is that all the provisioning is dynamic with API, and every cloud has its own set of provisioning and service delivery options and service keys that we need to manage too. And then for some of the clouds, like for example Google with GCI, it is a layer 3 peering cloud, and at the same time, a lot of people have private IP addresses that we needed to net. So that's the kind of problem set that we needed to solve for at a large global scale for hundreds of clouds inside our data centers. And I don't think anybody have had to solve for this before, because everybody built a single heterogeneous network based on their products to support point-to-point across the globe. We were the first place where what we call interconnection started to happen. So what did we implement? We implemented Juniper MX960 switches to support all this layer 2, layer 3. I'm going to show you some more detailed pictures of what we did. But the key features we really had to do was the Q&Q for that with flexible features because of the C tag and S tags. A lot of the traffic came to us aggregated behind service providers, or sometimes the enterprise came directly, and then on the other side, there was a lot of assignment of the VLANs inside the clouds that we needed to match up. We needed to use EVPN with multi-protocol BGP because we needed to preserve the MAC addresses and be able to create a layer 2 mesh, given the number of clouds are significant. And inside a metro, if you think of Equinix in a place like Silicon Valley, we have something like 10 data centers, all the way from Santa Clara, Palo Alto to San Jose. All of these needed to look like a single data center with all these different clouds and networks showing up in them. So we really had to do a layer 2 distribution. And then we also had to do layer 3 multi-protocol BGP control plane because of all the layer 3 routing, given the fact that a lot of people consumed VPCs inside these clouds. We needed to peer with all the enterprises and CSPs, and all of them came with their own IP address challenges. And this is what we did, the flexible net design. And that net design needed to be survivable, so we don't black hole any traffic in the case of any outage. So it wasn't just enough to net it. We had to net it even during an outage because of a lot of that address was private, and we needed to make sure that traffic was highly survivable. So that kind of a problem set, this is what we use, the MX960s and the design, which I'll walk you through. And then on top of that, we used Tailif, which is now a Cisco company, for orchestration and automated provisioning, because it wasn't good enough to be able to provision this in days or minutes. Everything needed to be automated with an API. We designed our own API integration with the CSPs and our own software platform for how we do that to be able to normalize for all the different service delivery models. And then what we did, we created a new operational model with detailed processes between the network operating centers of all these different clouds and ours. So if somebody had an outage or a situation, we knew who to call and what to do and all of it. So now step back and think, hundreds of clouds in 44 cities around the world with hundreds of networks and all these enterprises coming in, and you start to understand the magnitude of what we needed to solve for and why we did this. So on the layer 2 interconnect, the biggest thing we really needed to solve for was that VLANs were assigned at both ends before they got to us. So somebody may have used AT&T or Verizon or, let's say, Deutsche Telekom. They already had a VLAN addresses as part of that service provider, and we needed to do the Q&Q. And on the other end, they went to the cloud. Let's say they went to Microsoft Azure, and they already were assigned a VLAN there. So what we needed to do, bridge between the two, make the translation and make it redundant. And this is a simple layer 2. But we also needed to do it between multiple data centers because the customer, the customer service provider could be in one data center, and another data center in the metro was the cloud that they were trying to get to. On the layer 3, same thing, except we have now private IP addresses with VRFs for the customers at the PEs. And then the biggest challenge was definitely the net. We had to spend enormous time on the net to make sure that it was survivable both ways and match with the CSPs. And that really unlocked so much business for customers, because most enterprises have a very difficult time being able to map the IP addresses to connect to the clouds. And a lot of them had to do is create a single link to every single cloud. What we now with Cloud Exchange, what they do is be able to just create new VLANs or new outing instances on the fly with APIs as they needed to connect it to more clouds, which, as you know, most enterprises have to connect to 50 or 60 clouds. This is the framework that we did for API and provisioning and automation, which we would call this our phase one, because we are planning to use much more open source software now to fully optimize this, which I'm going to show you. But what we did is we took all our networks, which is at the bottom of this chart, including internet exchanges, cloud exchange, and we had an Ethernet exchange. And then we also have a whole virtual router as a service and a VNF aggregation design. So we had to take all of that and then create a controller layer on top. And from those controllers, we created configurates for provisioning from a service orchestration module with APIs. And then above it, we had a whole API framework that gives people access not just to the networking components, but people want to be able to use APIs for billing, fiber cost connects, being able to do something called DCIM, which is the data center information management, infrastructure management. So long story short, people wanted to come to us with APIs to do everything they do for us, with us from billing, provisioning, and then part of the APIs is used for orchestration and provisioning of services, both layer 2 and layer 3. And so all these services that we created for people, from netting to layer 2 cost connects, virtual cost connects, we created them as configurates that people could use in this network service provisioning layer. All of that had to be done by ourselves manually because there was nothing on the market that we could use. The only thing on the market was Taylor from Cisco for the disaggregation, at the controller layer that we used. So another piece of the process was, after this architecture was available, we had to sit with every single cloud and figure out the end-to-end provisioning process. And I'm going to walk you through one now with, let's say, this is what, if you buy service from Azure as an enterprise customer, is what it would look like. So you can get a sense what these service delivery processes look like. So if you're an enterprise and now you want to buy IaaS service from Azure, and they're in all our data centers all over. So first thing you do, you come to our data center and you get a cage and you say, I'm going to put my equipment there because I want direct fiber connectivity. And then after that, the enterprise would go to the CSP's portal. So let's say it's Azure in this case, and they would go on the web, and they would set up all the service, and they would ask, inside the service, they would have an option that says Equinix private connectivity. That Equinix private connectivity option wasn't even there. With every one of these big clouds, we spend months working with them to create this private connection Equinix as a new service that they can have available. So once that happens, customer can select it, and then the CSP would give them authorization key for that customer to now connect privately inside Equinix. The next thing the enterprise does at that point is they go to our portal or uses an API, and they give us that authorization key that the CSP, like Azure, has given them. Once we do that, we actually send that, we come back to the customer, and we give them the virtual cost connect parameters that they need to have, the VLAN ID, et cetera, so they can connect to our cloud exchange. They would have physically ordered a fiber cost connect and a port, but now they need the virtual cost connect. Once they do that, we now communicate back with the CSP to say, now we have this customer that wants to connect to you, and we give the CSP the authorization code that they've given us. They come back to us, and we complete the loop, and we send the customer authorization all the way to connect to our virtual cost connect. And then, as you can see in number 8, we connected end-to-end. So does that make sense? Without walking you through piece by piece, basically, customers go to buy the service from the cloud. They get authorizations. They come back to us. We validate it with the cloud provider, and then we give them VLAN IDs so they can connect. The same process is used every time somebody uses a cloud, no matter how many clouds they want. And sometimes they use it multiple times with the same cloud if they're buying multiple services. So let's say you're buying Office 365 on the cloud. That's different than Azure IS. That's different than some of the other services that you might buy. Normalizing for this process with APIs allows them to be able to buy it quickly and activate it. All of this was manual 3 years ago for every cloud, just to get a sense of what people went through. And now, so here's what it would look like. All the way on the left is what the customer deploys in our data centers. They have their routers, and now they have connections to our Cloud Exchange. And so the first thing they do is once they connect our Cloud Exchange with the VLAN ID, and we connect it all the way here into AWS, they would create their own BGP routes and connect the dots and be able to create the VPC inside AWS and use it. You can see in this case, they chose to connect to 2 different Cloud Exchange nodes for diversity and created 2 different connections to AWS so that they don't have an outage in case of any situation. Now, if they also want to connect to Microsoft Azure, which these 2 are the most common we see in our data centers, people connecting to those 2, and then they connect to many more once they start with those 2, including Google Cloud. What happens once you do that, from the same port that they have on Cloud Exchange and the same VLAN, now they can add more connections to Microsoft Azure and create more routes. And they can do that as much as they want, as many as they want. They can create those in minutes, and they can also take them down in minutes. So we see customers who are connecting continue to create a lot of virtual cross connects, continue to take them down as they need to, and they can do this in 22 markets around the world with us and be able to connect to hundreds of clouds. So here's what the picture looks like now, and it's still evolving. To me, this is what the globe looks like in terms of connections for enterprise and how they're moving on this cloud journey. All the way on top is the metros or markets that we have. So this would be Atlanta, Chicago, Dallas, if you can see it. And all the way at the end, you see Tokyo, Osaka, Sydney. So these are our symbols that we use. So we have, in all these markets, we have multiple participants and service providers. In Atlanta, we have 8 service providers. In a place like DC, which is the most mature market, we have already 157 companies, clouds or networks automatically connected to Cloud Exchange for that API automated provisioning. The dots, the squares that you see shows that not only do we have the connection, but we actually have the physical deployment of the cloud edge in our data center. That's really important because people not just want to connect, they want to be able to get to the compute edge with high performance very quickly, especially for multi-cloud application or hybrid storage, analytics, or anything like that. They don't want to be able to, they want to connect and be able to scale all the way to 100 gig if they wanted to. So that collection of cloud edges doesn't exist anywhere in the world but in the data centers that we have right now. And we worked very hard, and we continue to work hard to get more of those in. You can see companies like SAP and even Oracle now and Salesforce are starting to deploy more edges. You can see it in the light blue. So more and more we see this happening. As I said, we have hundreds, so we have pages and pages behind this one, but you get a sense. The thing we observed is that once people connect directly to our data center, the volume of services that they use goes up by 10x, because suddenly the performance is fantastic. They feel very comfortable building hybrid cloud. The next biggest things we're starting to see is that as storage goes to software-defined storage and people are building data architecture, especially for converged apps that need to do high-performance analytics and decisions on the fly, those are the ones people use for IoT. We see the biggest need there to connect to multiple clouds, to exchange data, to pull different data that's live, and be able to make decisions quickly. So this is really not just important for compute, but more and more it's going to be more important for the data architecture and analytics as compute starts to become very distributed with IoT and go all the way to the edge. This is something we're going to continue to work on and expand and enhance. So what do we see coming up? This is why we really are very interested in everything coming out of TIP, and why we're very engaged in that with Hans-Jürgen and team. A lot of the solutions coming out of TIP actually help us scale what you saw before. What you saw before was we solved it with today's technology, but think about all these different providers, plus thousands of people going to SDN and NFV, everybody from NetApp announcing that now the service is available as an NFV at OCP, to all the security companies going to an SDN model, and even the big networks, each one of them going to SDN, means that this thing is going to become very unmanageable at the physical layer in the long term. So all these things that we have tested within the TIP environment are all in the works for us, especially using SnapOut as an open source software on top of Voyager. And we tested a lot of these. Also, from a hardware perspective, we're definitely behind the OpenAG v2 so that people can mix and match hardware and software in our data centers to solve this issue in the long term. And here's our goal for disaggregation, the things that we really care about. So as things go to software and become all these providers that you know about become either software only or hardware only, we are engaged in TIP. We are very focused on enabling high-speed or very high-speed data center interconnection using the open packet white boxes, open line systems, and also open network software. Also, in terms of multi-cloud connectivity, this is where we're really interested in open network routing, which is something I think we'll start to create within TIP in the near future. We do want the programmatic control of interconnection using open source with API integration, and we are looking at what OCP innovation we can take advantage in our data centers to scale the fabric and interconnection at high speed. So all these things, piece by piece, we're going to bring into our architecture over time. So we are starting a lab now in San Jose here, which is one of the most dense data centers we have, to put all the TIP open and OCP open source hardware so that we can start to test interconnection. All the issues that we solved before, we want to see how can we solve it from an open source model at high scale. And this is our architecture that we deployed. The thing that's most interesting to us is being able to use Open Linux and being able to have all these software components from layer 2 to layer 3 programmable at the software level. This is probably the biggest benefit that we see, and companies like SnapOut and others that we tested provide all of that. Because once you have this programmability of all this layer 2 and layer 3 functionality, a lot of the issues that we talked about before in being able to create a layer 2 mesh or with EVPN or layer 3, a lot of these things become much simpler, and you can do the interconnection inside the same box. Everything also from the hardware is becoming programmable and open from the ASIC, FPGA. Also, the CPU allows you to put all the software on it, and that's what we want to enable. The test case that we tested, and we want to make it live and available for a lot of people, is this one, which is being able to, for all these companies that we talked about connecting to us, would like them to be able to bring in the SDN controller and program some kind of an open switch to connect between any cloud to any cloud, any network to cloud, and also any enterprise coming in to connect to any of them. And you could see here one use case we have is the data center interconnection. Anybody can write a rule and be able to use the SDN controller with the APIs to open source software like SnapOut, and switches like the Voyager. They'll be able to create the connectivity all the way to the DSP chip, to the transponder, and connect anything to anything. So that's kind of what we see next, especially if everything goes to SDN and software. Think of a company of our size and the thousands of networks and clouds that we have, and that gives you a sense of how this really becomes the place where the world starts to solve for the explosion of software-based networking components. I hope this made sense. Thank you very much. Yeah, thank you.
Thank you. Have great presentation. I mean, the progress made in the last 2 years, just amazing. So 2 questions. One on quality of routing software in open source community, especially more complicated things such as EVPN, which is probably like 40 many years of development. Do you see this getting to the point it's actually deployable and sustainably deployed? You could use it.
Yeah, it's not there yet. I think the reason we went with the traditional architecture with EVPN and also with the multi-protocol BGP is because those are stable, and what customers are looking for is high security and high performance and predictable performance. So, and we don't have monitoring and network management tools for any of those. But I would say so far, it looks, they have these open source software with open hardware that's programmable, have significant potential. Because now, with the way it's designed, you can pull all kinds of data out of the CPU to manage the network, get real-time analytics we couldn't do before. What's also very important is the clouds have gone to a fully automated model, as we've seen here. So being able to keep up with the automated template pushes from all the different cloud providers as they change the APIs is no longer possible with the traditional networking model. So we have to go down that path. The quality is not there, but we're going to work very hard at creating a lab so that we can have this multi-hardware, multi-software vendor testing environment to start happening, and then we can really vet these quality issues.
Thank you. Number 2 question. So you've used NSO to implement the data modeling layer, and it's great you deliver your knowledge how to work with clouds on one side and with vendors on the other side to NSO. You're consuming a lot of open source software. Do you have any plans to kind of open source data models, enhancements to existing service models into open source world?
Yeah, we definitely would do it. I don't think right now we have anything that we feel is very unique at this time yet. But I think what's going to be really unique is that when we get to the point where you'll have more networks and more clouds all align around the same architecture, we would definitely open source that. The way I see it happening is the big developments like AT&T with ONAP and having all these networks. That may be one open source module that we also support, and then that becomes something the industry can use. Or what Google just did with the SDN and being able to open up its SDN network for people to use. I think we would follow those leaders versus us setting the model.
Ihab here. So I have a question regarding to the quality of service. So because Equinix has definitely becoming #1 to connect people directly,
yep.
You're gaining the degree of connectivity, but at the same time, one single user will be able to choose which public cloud they prefer at what rate.
Yep.
So who should be responsible to guarantee this quality of service, especially at the layer 2 cloud exchange?
Yeah, we definitely guarantee that ourselves today. So this is why with EVPN and everything we deployed, we do have a QoS, and we do monitor the performance. One of the advantages we have is most of the connectivity happens inside the same data center. So we really have a non-blocking network, and we don't have a lot of contention. It's more about making the connection in and out than hauling traffic. And you'll see 80% of what people use in our data center is still fiber cross connects, where they feel they own the fiber from both ends and they can control their own QoS.
Can I say it's through the over-provisioning?
Big time, yes. And that's not an issue for us because we don't have to do a long-haul network. We have to do backhaul between data centers in the same metro. We buy dark fibers and connect them because it's a lot easier to solve it with fiber for these short-haul networks than any kind of contention design based at this time.
Thanks.
Yeah.
Hi, Ihab.
Hi, how are you?
Good, good. Great presentation. Thank you.
Absolutely, thank you.
Louis from Google Fiber. I wanted to ask.
And he was with Equinix before, and we love Louis.
Thank you. Being IPv6 Day, I wanted to ask, for the pieces that touch layer 3, do you have feature parity between v4 and v6?
Yeah, at this time, yes. And we had to go to v6. Most of the cloud providers use nothing but v6 for some of the services. So the answer is yes.
Wonderful, thank you.
Yep, and it's easy because this is a new platform that we just deployed. Thank you, Louis. Okay, well, thank you guys very much. Thank you. Thanks, Paul. Yeah.